Right. So for the remaining 40 to 50 minutes, we will look into the final section of this chapter, chapter 7, which is known as the prop fan or propeller fan engine. Okay. Of course, we will first look at the overview, then historical hints on where does this type of Propfan engine originated, classifications of Propfan, and finally a comparison between the Turboprop, Propfan, and the Turbofan type of engine. In terms of the overview, a Propfan is a modern type of aircraft engine which is related in concept to both the turboprop and turbofan. Basically, it is a combination of both, a turboprop, principle of engine, as well as the turbofan type of engine. But it is basically distinct from both. That's why it is in its own category, a propfan type of engine. The engine uses gas turbine. It is also part of the gas turbine engine family to drive an unshielded propeller, like a turboprop. Okay, but the propeller itself is designed with large number of short, highly twisted blades similar to the fan of a turbofan engine. Okay, basically it's a combination of a turboprop and turbofan. So for this reason, the propfan has been variously described as the unducted fan. If it is a turbofan, it is ducted fan. But for propfan, it is unducted because it is not enclosed within a duct. It is also known as open rotors, OR, or ultra high bypass turbofan, UHB. Okay, so let us look into the definition here. It is described as a small diameter, highly loaded, multiple bladed, variable pitch propulsor, and having swept wide chord blades with thin advanced airfoil sections integrated with a contoured nacelle. So that is what being described as the definition of the propfan. A propfan is designed to operate with a turbine engine and using a single stage reduction gear that results in high performance. So the design is intended to offer the performance of a turbofan at the same time with the fuel economy of a turboprop. So it get the best from the two arrangement of a turbofan as well as a turboprop. The most common arrangement of a propfan is a two-spool gas generator and aft-located gearbox driving a pusher fan. So this fan produces the majority of the thrust. Okay, it has a number of blades greater than the propellers of turboprop and less than those of fans in a turbofans. So similarly, its bypass ratio is also in between turbofan and turboprop engine. Let us look into the historical aspect of it. Okay, during the 1970s, due to the oil crisis somewhere in 1973, several projects for developing propfans or unducted fans, we will use this UDF throughout this particular section, were introduced. And the propfan concept was first revealed by Carl Rohrbach as well as Bruce Mercer of the Hamilton Standard Division of United Technologies in 1975 and was patented by Robert Cornell and Carl Rohrbach of Hamilton Standard in 1979. Later work by General Electric and GE company on similar propulsors was done under the name unducted fan, which was then modified turbofan engine with the fan placed outside the engine nacelle on the same axis as the compressor blades. Perhaps one of the most significant series of Propfan studied was conducted during the late 1970s and the early 1980s, and this effort culminated in flight tests of the McDonnell Douglas MD-UHB demo aircraft based on the MD-81 airframe. Right? So the MD-UHB was used to evaluate advanced experimental propulsion technologies, which was designed to offer airline significant improvement in fuel efficiency and lower operational costs. And the Propfan concepts was intended to deliver up to 35% better fuel efficiency than contemporary turbofan. That's a lot in terms of the fuel saving. In static and air tests on a modified DC-9 aircraft, Propfan reached a 30% improvement. That's also already significant. So this efficiency comes at a price, as one of the major problems with Propfan is basically noise. Noise is quite tremendous, particularly in the era where aircraft are required to comply with the increasingly strict Stage 3 and Stage 4 noise limitations. General Electric introduced its unducted fan, UDF GE36, which featured an aft-mounted open rotor fan system with 2 rows of counter-rotating composite fan blades during the mid-1980s. So it is of the pusher configuration. It pushed the aircraft forward rather than tractor type. And the core was based on the GE F404 military turbofan. Exhaust gases were discharged through a 7-stage low pressure turbine, LPT. Each stator ring was designed to move freely in the opposite direction to that of the rotors. The turbine rotors drive one propeller, while the other prop is connected to the unearthed turbine stators and rotates in the opposite direction. So in effect, the power turbine has 14 stages, quite a lot there, as shown in figure 722 over here. So open rotor with counter rotation achieved via statorless low pressure turbine. So you can have an arrangement where the turbine system, this open rotor with counter rotation relays via statorless low pressure turbine. Okay, you have the compressor stage over here, connected to the turbine system, compression system, high pressure compressor connected to the high pressure turbine, and this is the power turbine, which is actually a free power turbine. This is a counter rotation open rotor outside of the engine, outside of the nacelle. It is basically one rotate clockwise, the other rotating anti-clockwise arrangement. The GE36 flew on Boeing 727 type of aircraft, and MD-80 aircraft enable speeds around Mach 0.75. The McDonnell Douglas already developed a proof of concept aircraft by modifying their MD-80, and they actually removed the JT8D turbofan engine from the left side of the fuselage and replaced it with the GE36, as shown in figure 723 over here. Okay, there's a engine ultra unducted fan installed in the MD-80 McDonnell Douglas aircraft. Okay, so it is even though it's heavily noise generated, but you can see that it is sitting at the back of the aircraft, at the aft of the aircraft, where passengers probably not experiencing the noise, but the the people outside can easily hear the noise coming out from the engine, because it is quite noisy. A number of test flights were conducted which proved the airworthiness, aerodynamic characteristic, as well as the noise signature. It is still a significant noise generated. The tests and marketing flights of the GE outfitted demo aircraft, which concluded in 1988, demonstrating a 30% reduction in fuel burn over the turbofan powered MD-80. A full stage 3 noise compliance and low levels of interior noise vibration due to jet fuel price drops as shifting marketing priorities. Douglas shelved the program the following year. It's not went into the market. In 1980s, Allison collaborated with Pratt & Whitney on demonstrating the 578DX Propfan, having a reduction gear between the low pressure turbine and the Propfan blades. So the engine itself was successfully flight tested on a McDonnell Douglas MD-80 as shown in this figure 724. Okay, this is a Allison Pratt & Whitney 578DX geared Propfan schematic diagram for the open rotor with counter rotation relays via power gearbox. Okay, there's a gearbox connected the counter rotating open rotor, right? The Progress D27 Propfan in figure 725 developed in the USSR is even more conventional in the layout, with the Propfan blades at the front of the engine in a tractor configuration. So it is used for propelling Antonov AN-180 and AN-70 aircraft in the 1990s. It is worth mentioning that the only flying aircraft powered by Propfan engine is the AN-70. This is gone into the manufacturing stage and being used in the Russian Federation. Rolls-Royce is also testing its contra-rotating Propfan known as RB3011, which is planned to fly by 2020, but it's not being realized in year 2020. So this is the AN-70 aircraft powered by the tractor type contra-rotating Propfan. So you can see that it's nearly touching to each other, but if you look at the side, it has some clearance between the contra-rotating Propfan as being highlighted here. Classification of Propfan. Our next segment for Propfan engine 7.4.3. There are two main types of Propfan. One is the tractor type and the other one is the pusher type. With regard to the tractor type, or known as the puller type of Propfan, it sits in forward of the fan at the front. That is the function is to forward fan with the fan placed outside the engine nacelle. We will show it in figure 723. And the Propfan are normally of the wing installation type. Okay. Also, such arrangement dictates a high wing design. Okay. So this type is next divided into single, or the other type is contra-rotating or counter-rotating type of arrangement. An example is the contra-rotating Propfan installed in AN-70 type of aircraft, as shown already in figure 7 to 6. The forward rotor is 8-bladed, while the rear is normally 6-bladed. Okay, so tractor type of Propfan, so you have the Propfan in front and reduction gear. There's a top lean, structural upper inlet. We have the engine installed there. Okay, and this is quite complex arrangement. And for the type B, the contra-rotating, so you can have the two Propfan arrangement, one clockwise, the other one is clockwise arrangement, right? The pusher type Propfan is similar to the aft fan where the fan is coupled to the turbine. It is always of the contra-rotating type, as shown in figure 27 later on. The two fan rows are driven by free power turbine. So this type would be more elegant, as the engine would be placed behind the rear pressure bulkhead in the fuselage. As what I already explained earlier, it will minimize noise to the passenger. And it also would allow for an aerodynamically clean wing because it is being placed at the rear of the aircraft. Right, so this is a pusher type of Propfan, okay, shown in figure 7 to 7, right? Engine and aircraft accessory in the front, where you have the propeller setting, Propfan at the rear of the engine.
Here's what I found.
Okay, and then for the 744, comparison between Turboprop, Propfan, and Turbofan. With regard to the Propfan engines, which have the best ever known propulsive efficiency, single rotation Propfan engines have propulsive efficiency around 80%, right? While contra-rotating Propfan ones have higher efficiency, close to 90%, right? So this is with regards to propulsive efficiency. And the main features of the Propfan versus both Turboprop and Turbofan engine are given in table 7.1 over here. You can see the comparison between Turboprop, Propfan, and Turbofan HBPR, engine high bypass ratio type of engine. So you can, in terms of the number of blades, okay, Turboprop 3 to 6 blades, Propfan 8 to 12, Turbofan, this is for fan blade, 20 to 30 blades. Diameter, of course, Turboprop is the largest. The Propfan is quite medium, small, and Turbofan diameter normally the smallest. Power square diameter comparison, blade shape, right, nearly straight for Turboprop. Propfan swept and scimitar-like profile, whereas the Turbofan is a swept type of blade shape. Thickness, okay, thick, thinner, and the thinnest. Tip speed, subsonic, supersonic, and supersonic for Turbofan. Bypass ratio, nearly 50 for Turboprop, 25 or more for Propfan. For Turbofan, 4 to 12 bypass ratio. Propulsive efficiency, okay, Turboprop having the highest high Turboprop efficiency, propulsive efficiency. Propfan higher, and Turbofan propulsive efficiency is lower. The equivalent specific fuel consumption for the Propfan, it consume less fuel, right, compared to Turboprop. Okay, well, for Turbofan, of course, we do not have equivalent specific fuel consumption for it. Mach number, it operates around 0.68, and operating cruising altitude, it can go similar to the Turbofan engine. However, the open rotor presents many technological challenges. These are disadvantages, and the challenges need to be addressed by researchers around the world, including noise and vibration, because it is outside, and the arrangement of the fan is outside. Okay, it noise and vibration can be experienced both inside and outside the aircraft cabin. Structural reinforcement of the fuselage and wings that require the aircraft to be more heavier, okay, and it will cost a lot for the aircraft in terms of the costing. airworthiness consideration, blade off, suddenly blade flying off the engine, and there's a lot of issues over there. Engine installation and mounting issues, gearbox cooling and reliability, design of efficient counter rotating components, the bearings and the gearbox, and so on. Competing technologies such as the efficiency of current technologies of the engines is improving at an average of 1% per year, which means traditional turbofan engine available in 2020 are likely to be at least 11% more efficient than the one that being produced earlier, like in the 2010 production models, without any major technology risk. Okay. Meanwhile, Pratt & Whitney company produces PW1000G geared turbofan that could provide a 22 to 23% fuel efficiency gain by year 2017. So this is also keeping up with the fuel efficient. According to the company of Pratt & Whitney, right, that is what being claimed by them. And while CFM International produces the non-open rotor LibX design, which already provided 60% lower fuel consumption compared to the old CFM 56-7 by year 2018. So some manufacturers are skeptical about open rotor technology. Okay, so that's another issue. Slower aircraft operating speeds, and an open rotor powered aircraft is likely to have a cruising speed around 5 to 10% slower than a turbofan powered aircraft. The Propfan engines have the highest propulsive efficiency, the potential to significantly reduce fuel consumption and emission relative to state-of-the-art high bypass ratio geared turbofan engine, which is much more popular. And moreover, in terms of the benefits to the aircraft operator or the airlines and the environmental impact relative to today's aircraft, a future open rotor powered aircraft could save approximately $3 million and 10,000 tons of CO2 per year per aircraft. That's quite huge. And further considerations need to be given to the trade-off between fuel burn and noise, right? So that is something to ponder for engine designer. Let us look into example for calculation. A 3-spool pusher type prop fan or unducted fan engine UDF is fitted to an aircraft flying at a speed V of 220 meters per second. The altitude is given at 6 kilometers, where the value of the ambient temperature 249.2 Kelvin and the atmospheric the pressure, the ambient pressure PA equal to 47.182 kilopascal, as shown in figure 7 to 8. The engine is composed of 3 spools, and we have intermediate pressure spool composed of intermediate pressure compressor driven by intermediate pressure turbine, a high pressure compressor driven by high pressure turbine, and the unducted fan resembling a low pressure compressor driven by a low pressure turbine. So the maximum temperature at the combustion chamber is 1400 Kelvin, and fuel heating value Q equal to 40,000 kilojoule per kilogram is used. It has the following particulars, right? So you have the mass flow rate, the intermediate pressure compressor ratio, high pressure compressor ratio, the unducted fan compressor ratio, the combustion chamber pressure drop, the efficiency of the diffuser, efficiency of the intermediate pressure compressor, efficiency of the high pressure compressor, efficiency of the combustion chamber, efficiency of the intermediate pressure turbine, efficiency of the high pressure turbine, efficiency of the fan turbine. Then you have the efficiency of the the engine itself, the zeta n there, the efficiency of the unducted fan, efficiency of the mechanical of the unducted fan, the alpha, the bleed ratio B, specific ratio at specific heat ratio at constant pressure for the combustion chamber, and for the turbine, which is equal to the and the nozzle itself, 1.148 kilojoule per kilogram Kelvin. There's so many parameters given for you. Right. What you need to do is basically to calculate the bypass ratio, beta, then ratio between thrust force generated by the unducted fan and the nozzle. Okay. The total equivalent horsepower, EHP, and the propulsive efficiency, zeta P. The station, again, the states are a lot. We have from A, number 1, until 12. Okay, layout of a Propfan unducted fan engine. In terms of the solution, we already show, we are going to show you the figure 7 to 9, which illustrate the TS diagram for different states as highlighted in figure 7 to 8. And we start with the intake. We have state A to 2. The engine is examined during flight speed of 220 meter per second, altitude 6 kilometer. Then the total condition at diffuser outlet are calculated as follows. Using equation for the flight Mach number, right? You get the A equal to 316.4 meter per second. You get the Mach number is around 0.695. You then obtain the temperature at state 2 equal to 273.3 Kelvin, right? And the pressure is given, is found to be 63.56 kilopascal. Moving into the IPC, intermediate pressure compressor, state 2 to 3, you then get the value of P03 to become 197. You put the pressure, intermediate pressure compressor ratio to be there, okay, 3.1, okay, and then you will then get temperature at 03 to become 397.68 Kelvin. This is basically the TS diagram. There are so many stations from A, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 stations. Okay. Moving into the high pressure compressor, state 3 to 4, high pressure compressor ratio times the P03, you get P04, 1103.2 kilopascal, and T04 temperature equivalent to the 695.4 Kelvin. In terms of the combustion chamber, state 4 to 5, P05, you have the pressure drop in the combustion chamber. Okay, then you get the pressure at P05 and the fuel to air ratio. You have the value of the bleed, okay, and all the corresponding specific capacity at combustion chamber, compressor, the bleed, and the combustion chamber over here. You get the value for the fuel to air ratio as 0.0216. Moving into the high pressure turbine, state 5 to 6, using energy balance for high pressure spool. So you have the energy balance at state 3, 3 and 4, and 5 and 6. Okay, you then obtain the T06 value at 1110.8 Kelvin. Moving into the pressure, you can then obtain the P06 value of pressure 379.75 kilopascal. Moving into the next state, state 6 to 7, intermediate pressure turbine, using any energy balance again, you will then obtain T07 to become 1004.3 Kelvin with the respective pressure P07 to become 243.26 kilopascal. Moving into the unducted fan, UDF, state 10 to 11. So T10 equal to T2, which is 273.3 Kelvin. And then you immediately get the P10, right, to become 65.15 kilopascal and P11 to become 71.54 kilopascal. With regard to T11 now, you will then use the values of the compression ratio at the unducted fan, okay, and efficiency of the unducted fan given already earlier. You can get the value of T11 to become 282.3 Kelvin, right? So eventually you can then get the value of T12 to become 250.6 Kelvin. That resulted to the exit velocity, UE, of the unducted fan to become 252.4 meter per second. With regard to the free turbine, state 7 to 8 and the hot gases nozzle, state 8, 9, right? So we have T07 of a ratio with T9, okay, and then which is equal to the P07 over PA. You can then get the ratio to become 1.5068. Eventually, you get the value of T9 as 666.5 Kelvin. Temperature drop in the free turbine, T7 minus T08, right? So you can then get T08 value to be 740 Kelvin, T08S equal to 717.2 Kelvin, right? So eventually, you will then get P08 to become 63.14 kilopascal, where the exit velocity at the nozzle to be 402.5 meter per second, right? So just now, velocity for the unducted fan, and now you have the nozzle exit velocity, 402.5 meter per second. So the thrust obtained from the exhaust gas leaving the nozzle is denoted by Tn, total thrust. So you have the component of the exit velocity at the nozzle and exit velocity at the unducted fan as well, right? So you get the total thrust to become 7,648 Newton. This is the thrust from the prop fan as a whole. With regard to the energy balance, you want to find the bypass ratio, beta, using all the information, putting in the numbers, you get beta value to be 33.58 value. The thrust force obtained from the unducted fan, TUDF, given by this equation, the thrust from unducted fan, you already get beta. You can then provide the calculation to become 43.525 Newton. Hence, the total thrust from the unducted fan plus the thrust generated by the nozzle, okay, Tn equal to 51.173 Newton. So this is the overall thrust produced. Now, the ratio between the unducted fan and the nozzle thrust, TUDF over Tn, you get 5.69. the power generated by the unducted fan is equal as the velocity times the thrust produced by the unducted fan. It's actually for the unducted fan itself producing a power of 12,842 HP. Okay. Now we want to calculate the propulsive efficiency, the final part of the question, looking into the propulsive efficiency, right? Putting the numbers using this expression for propulsive efficiency, you can then obtain 94.247%. Right. As a summary, so we now already completing our chapter 7. Chapter 7, which already focuses on the 3-shaft engine, namely the turboprop, okay, which we have already covered last week. Today we cover the turboshaft and the propfan, right? So we also look into example that describing the thermodynamic behavior, the performance analysis of the each type of the engine also discussed. At the same time, I already brought you the examples of the manufacturer, as well as the type of engine for turboprop, turboshaft, and propfan, and where does the technology is going for all the 3 type of engine. So that wraps up our topic on chapter 7, turboprop, turboshaft, and propfan. That leads us to the last chapter, which is the propulsion system characteristic. Okay, so chapters 8 will be covered in lecture number 14 and number 15, right? As highlighted, I've been informed by Dr. An that on the 29th will be the Vietnam National Day. There will be a holiday, right? So meaning that we are not going to have our session on Monday next week. We will try, I will discuss with Dr. An to find a suitable replacement class for lecture 14, and we'll try our very best to fit it next week. If not next week, we will try to combine it in the week after, where we have lecture number 15. So I'm looking forward to see you in the following lecture. Okay, so again, thank you for your attention. I realize that we have already reached at the end of our subject, and nearly to the end, and some of you have already viewed the YouTube videos available, and I will make the video for the lecture number 12, and hope that I can also provide you video on lecture today, lecture 13, as soon as possible. So that ends up our session for today. See you, all of you, in the lecture number 14, hopefully next week or the week after. Okay, stay safe. Thank you very much. Have a good holiday next Monday for your National Day. And bye-bye for now.